Yeah, so I've attended many of these seminars, and I think it's a great seminar series, and I'm happy to be able to present here today. Mark gave already a really great summary of the research that we do in my lab. My lab is the Multi-Robot Systems Lab, and lately, actually, most of what I'm talking about in my talk today is not multi-robot. In fact, I'm trying to think if there is any multi-robot. I think there isn't. Lately, I've been really fascinated with NeRFs, neural radiance fields, which you'll hear all about in this talk. And not only NeRFs, but associated rich, deep neural network-based, data-driven 3D environment representations and what they have to offer robotics and how do we integrate them into the robot autonomy stack. So if you're not familiar with a NeRF, I'm sure many of you are by now. NeRFs are, I use the term NeRF as kind of a catch-all term. There's a specific thing called a NeRF that was introduced in a paper in 2020, but by NeRF I really mean all kind of vision-based light field representing models that try to capture 3D structure and 3D light fields for a scene. So this is an example of a NeRF. This is Old Union, as you can probably tell, which is a building complex here on campus. And this is a deep neural network that you can image in a way that I'll discuss in a minute. So all of the information you're seeing, even though it looks like a video feed, is actually stored in the weights of a deep neural network. And that deep neural network is trained by images taken from a regular iPhone. So one of my PhD students took out his iPhone, walked around the courtyard of Old Union, and then took the images, fed them into what is now a fairly standard training pipeline, and this is the model that emerges. So you can see that the model allows you to kind of interact with the world in a video game sort of way, right? You can sort of free fly a virtual camera around the scene. And so this gives you the capability to predict what a camera will see if it's in some part of the scene, and it also gives you the ability to reason about the 3D structure of the scene and to close feedback loops and to do planning and to also reason about semantics and object level reasoning and do all these really exciting things that were not possible before. So that's the main idea, is storing 3D environment geometry and lighting and richer maybe semantic information in a neural network. And so in this talk I'll talk about scene-wide representation as well as object-centric representation. They're very closely related. In both cases, the concept is represent the geometry and the lighting as a neural network. So what's new here? Why can't we do this with existing geometry or environment representations in robotics? I would argue you kind of can, but it's just really clunky and multifaceted, lots of different interlocking parts that become very elegantly streamlined if you treat this as a neural environment representation. So what are the existing representation architectures in robotics? Well, and also in computer vision. So the standard in computer vision is a triangular mesh. This is the workhorse, the backbone of all computer graphics and computer vision, you could argue, until maybe 2 or 3 years ago. So if you watch a CGI movie or a movie with CGI effects, those effects are produced by a triangular mesh. So it's an extremely rich representation, but it's actually pretty rare in robotics to deal directly with triangular meshes. And the reason is because it's difficult to build triangular meshes online from robot sensing data. It's great if you have complete control of the model and you're constructing the model in a graphics engine. That's great. But if you're actually building a model to represent the observed natural world, it's difficult. It's difficult to correct these models if mistakes are made, and it's difficult to reason about uncertainty with these models. And so they're typically not used in robotics. Instead, in robotics, we tend to use point clouds, which are the natural representation if you have LiDAR sensors or RGBD sensors, and voxel grids, which is a really natural representation if you're doing planning and you're worried about safety. And oftentimes, both of these representations live together in an autonomy stack, right? So maybe your sensors induce a point cloud-based map, and then you process the point cloud map to get a voxel grid representation, and then you do planning and control on the voxel grid representation. So what's missing in these two standard representations? There's no light information. There's no way of taking the very rich color and texture and context that comes from an image and somehow reasoning about that in the 3D scene. It just doesn't exist. It's all geometry, 100% geometry. Also, Point clouds, you can't carefully reason about collisions in point clouds because everything's free space except for these little singular points. And voxel grids are in some sense storage inefficient. You can make them more efficient with clever oct-grid style representations, but they tend to be storage inefficient, and they're kind of over-approximate geometry representations, right? Everything is either a big block that's there or not there. And so they tend to lead to over-safe maneuvers. And neither of these representations do a very good job at handling uncertainty. And so my pitch here is that neural representations maybe, it's early days, but I'd like to believe that we can go a lot farther with neural representations by covering all of these deficiencies that exist currently. And furthermore, you can get point clouds and voxel grids out of neural representations. So they're, in some sense, kind of a unifying representation. OK, so let's get into a little bit of nuts and bolts about NeRFs. Exactly how do you store the light field in a neural network, and does storing the light field actually help you with 3D geometry and avoiding collisions? So the paper that introduced the NeRF concept is listed here. It came out of Berkeley a couple years ago. Super influential paper. It's already got thousands of citations. This was a really seminal paper, I would say, in computer vision. So the idea is you have a fairly small, typically a fairly small neural network, usually a few layers, something like 5 to 7 layers of 512 neurons. They're all standard, usually ReLU neurons, except for there's some special neurons on the first layer. These are all details. The main idea is that this neural network stores a map which goes from a 3D query point in the environment. So you ask, right here, that's the query point, and then a viewing direction. So I'm looking at that point from this perspective, or from this perspective, or from this perspective. You have a point and a viewing direction, and then the neural network spits out a density, which is basically it can be interpreted as a differential probability of occupancy. So think of it as a continuous version of an occupancy grid, and radiance, which is just the RGB color vector. So at every point in the 3D space, this function tells you the probability that that point is occupied by something and the color that that point appears as from a certain viewing direction. This alone doesn't give you the ability to produce images, right? This is just this volumetric model of the light field and the occupancy field. So the NeRF is paired with a volumetric rendering scheme, which is more or less a standard component in graphics and computer vision. It's called ray tracing. And what you do is you computationally pose your camera. You say, I want my camera to be imaging from this perspective. And you draw a ray from the focal point of the camera through one pixel. And then you go along that ray and sample your neural network. You say, what's the density and color here? What's it here? What is it here? What is it here? And at all of these points, you get a density, which tells you a weighting, and then the color, which is the color that you want to appear on that pixel. And then you combine these weights and these colors in, I'm going to say, a weighted average. It's not exactly that. There's something a little more sophisticated, but conceptually it's a weighted average. So you take that weighted average and you get an expected color. And so if you have a lot of gray sample points with high weighting and a couple green sample points with low weighting, you take the weighted average, it's roughly gray, and then you image the pixel as being gray. Right? You do this across all the pixels in your image. You define the resolution of your image. It's a continuous representation, so you can have a super coarse image, an extremely fine image. Doesn't matter. It's totally adaptable. And you get the just incredibly lifelike images. So the video feed that you see here is a sequence of images that was never taken by any camera. Right? This is the result of imaging this neural network. Now, the neural network was trained from images, from different images than the ones you're seeing here. So there are images, that someone took a camera and took some images and then trained the neural network and then now is generating fake images from perspectives that have never been seen by a camera. But you'd never know this. This totally tricks the eye. I don't know about you guys, but to me this is as good as real. Now, the ability to produce lifelike images is cool. It's a nice trick. But as a roboticist, I want to know about 3D geometry. I want to know if I can avoid hitting things, or if I want to know if I can go pick things up, right? And so what's maybe more surprising and more interesting as a roboticist is that this NeRF also captures very high fidelity 3D structure. As you can see in the bottom images, those are depth images. So I told you how to render color images. There's another pipeline for rendering depth images. There's another pipeline for rendering point clouds. This kind of primitive of the volumetric neural representation can be coupled with any kind of imaging sort of sensor model you like to produce synthetic sensor data. Okay, so there's a lot of good 3D structure in there. How do we pull it out, and how do we do planning safely, and how do we do, think about manipulation, or think about maybe interacting with the world at a higher semantic level of abstraction, these kinds of things. So those are the questions that I'll address in this talk, and I'm talking about research that we've already done in my lab, as well as work that's kind of underway. I'm showing you kind of hot off the presses results here. My lab, along with several other labs here at Stanford, have been sort of early movers in this space, kind of taking NeRF-type models and integrating them into the robot autonomy stack. But there have been a number of notable contributions that didn't come from my lab as well. So one of the earliest contributions came from Alberto Rodriguez's lab at MIT and Philip Isola's lab at MIT, and they came up with a really beautiful idea. This came like months after the original NeRF paper. I don't know how these guys work so fast, but they proposed a method called iNeRF, which says, okay, you've trained your NeRF, you have this NeRF. Now a robot or a camera, whatever, is in the world and takes a picture and has no idea where it took the picture. It just takes a picture. Can you figure out where the camera was to have taken that picture? And they solved that problem. That's called iNeRF, and I'll be building on some techniques that are based on iNeRF. Another paper that came out actually before the NeRF paper was called IMAP. Came from Andy Davison's lab at Imperial College London, I think. And they basically build a SLAM pipeline on top of not quite NeRF, but something very much like NeRF. It's kind of a NeRF light, so to speak. And this, as I said, it came out before the NeRF paper. And then in the space of manipulation, there's been quite a number of works. This was just an early one that actually came also from Philip Isola and Alberto Rodriguez. And it was basically combining the concept of dense descriptors. If you're not familiar with the concept, not a big deal. It's basically the idea of learning a color map that matches to an object. So all forks, in whatever pose they appear and in whatever background clutter they appear, are through this neural network mapped to a color map, so that you can distinguish the prongs of the fork from the handle of the fork, and then that's useful for manipulation. So basically, they took NeRFs together with this dense descriptor concept and used the NeRFs to produce training data to make better dense descriptors. These are just a few examples. There's a lot more out there these days. There's been a real explosion in this field lately. So as far as work from my lab, I'm going to talk about 3 works that I'm really excited about. 2 of them have papers already. One of them is a paper in progress, and the lead author of that work is in the back here. That's I'll try to shout out the names of all the authors from my lab who have produced these works. So first question that came to mind when we started learning about NeRFs is, okay, great. Can we use the NeRF as a backbone for safe planning? Can we navigate a robot through the world based only on a NeRF map with some kind of assurances about safety or avoiding collisions? So let's launch into that to begin with. Can we plan safely through a NeRF? What exactly is the problem here? Why is it hard? Why might it be hard to plan safely through a NeRF? Well, typically when you talk about guaranteed safe planning, you're talking about a map representation that has definite occupied and free regions. So the occupancy grid is perfect for guaranteed safe planning, right? So you know what's occupied, you know what's free. All you have to do is make sure your robot stays in the free space. That's great. Maybe if your robot path is noisy, then you worry about the probability of your noisy robot intersecting with the free space, or with the occupied space. Great. The problem with the NeRF is that it doesn't represent free and occupied space. It represents a continuous density field, where roughly the density is high in places that are occupied and it's low in places that aren't occupied. But exactly how do you scale the density to pull out like a probability of occupancy? That was really unknown until we started digging into this paper. And this is not an artificial problem. So you might think, well, maybe in practice, right, the density is like essentially 0 here and then jumps up to essentially 100 here, and so we're just talking about minor details. That's not the case at all. In NeRFs, the density is quite squishy and well distributed throughout the scene. And the squishiness of the density, we noticed empirically, corresponds very much to the quality of your training data. So you have really a lot of training data right here, you'll get that crisp edge. But if you don't have as much over here, you'll get a very foggy and noisy field of density. So how do we deal with this noisy field of density? So here we have an example of a NeRF trained of a coffee cup. And we took test points and moved them through the density field and then plotted for each test point the density magnitude for each of these 3 test points. And you can see that the distribution of density in some of these test points is quite peaky, like the green one. In others, it's pretty spread out, like the blue one. And in all cases, it's very noisy, right? So if you're relying on a particular point estimate of the density, it's not a very reliable thing. So how do we reason about probabilities of collision in this kind of density-based model? So this is primarily the work of Tim Chen and a former student of mine, Preston Culbertson, who's now postdocing at Caltech. We thought hard about this, and we realized that the equations that describe the rendering for NeRFs, the model that I showed you that takes the NeRF and produces a picture, those equations really suggest that the underlying density field is actually the density field of a Poisson point process, which is a well-understood random process, which I'm going to explain very briefly. This connection wasn't previously made. We made this connection in a paper that's under review. So what the heck is a Poisson point process? Poisson point process is something that is described by a density field over some subset of R2 or R3 or R4 or R5, whatever. And the density you can use to induce the statistics or the probability distribution of finding balls that randomly appear in the scene. It's a little bit hard to explain. Let me explain what I mean. So suppose you have a query region A. So you have some subset of your larger space A. This potato-looking thing, and you want to know what's the probability distribution over finding any number of points in that set A. What's the probability there are no points, 1 point, 2 point, 100 points? Each one of those number of points has a certain probability attached to it. And that probability, it turns out, is described by a Poisson process. Not a Poisson point process, but the old-fashioned Poisson process. Which means that there's some Poisson rate which describes the probability that each of these numbers of balls appears. And that Poisson rate you would obtain by integrating the density over the set A. So capital lambda is the Poisson rate associated with the set A, and you obtain that by integrating lowercase lambda, the density, over the set A. Then you get the rate of the Poisson process, which has this kind of exponential, you get the probability distribution of the Poisson process, which is given by this kind of scaled exponential distribution here. So the higher lambda is, so the higher lowercase lambda is, the higher capital lambda is, and the more likely you're going to have a large number of balls in that set. And so why do we care? We care because we can calculate rigorous probabilities about collision or the severity of collision with a Poisson point process. So if you take the set of interest as being the set that's occupied by the robot body, right? You can then query the Poisson point process. So you have your robot body, you pose it in a particular pose in your environment, and then you ask the Poisson point process, what's the probability that there are no points intersecting with this volume? And that's a number. It's 0.99 or 0.2, right? And it's totally calibrated. That's really the probability of there being a collision, given the certainty or lack of certainty with which we've modeled the environment. So you can make draws, just like any other random process. You can take a draw from a Poisson point process. And if you take a draw from the NeRF as a Poisson point process, and what does a draw look like? It looks like a bunch of randomly distributed balls. It's a point cloud. So if you take a draw from the Poisson point process, which is underlying the NeRF, it looks like this. So there's sensible 3D geometry right in there. And the NeRF that we took the draw from is well, you see one of the training images up there. So it's from the the flight lab in the basement of the Durand building. We set up some pillars as features. We've moved a camera around the scene, trained a NeRF, and then we drew the Poisson point process from that NeRF. So this is one random draw. If I were to take another random draw, any specific ball would be located in a totally different position, but the bulk 3D geometry would be the same. So this is the nature of a Poisson point process. Any particular ball is randomly placed, but the overall structure of the scene emerges from all these different balls. And you see that there are what we call floaters. There are balls out there in free space, which indicate that there's a lack of information from the training data in those regions. We don't really know if that's free or occupied. Whereas where the dense balls are clustered, we know quite confidently that that space is occupied. So that seems like a useful tool, but why do we have any confidence that we can interpret the density of the NeRF as the density of an underlying Poisson point process? Well, this has to do with the rendering equation, the underlying equation that goes into rendering the images from the NeRF. So essentially, if you suppose that the environment is represented as a Poisson point process and you compute the expected color of a pixel, you get exactly the same equations as those rendering equations. So it's entirely by sort of template matching, right? If I start with a hypothesis Poisson point process, what is the color of a pixel? I get the rendering equation. And so that's the intuition. And then now, how does this tie with actually training of the NeRF? Well, so essentially, we interpret training of the NeRF as moment matching. So we're basically matching the expected value of the pixel color between the data and the model. And this is kind of a standard statistical, a standard way of doing density estimation, so estimating the parameters of an unknown probability distribution through a moment matching. Okay, so that's the kind of the theory backbone. So now we have a way of quantifying the probability of collision for a robot that's posed in a NeRF. We want to wrap that inside of a trajectory optimizer. So we take our standard optimal control objective function. Maybe we have some desired trajectory, which is x bar. We have the state of the robot, which we're trying to make follow x bar, but we want it to be safe. We have some penalty for control effort. We have the dynamical constraints of the robot. So maybe it's a drone, maybe it's a ground robot, maybe it's a mobile manipulator, maybe it's an autonomous car. It doesn't really matter. It's just some dynamical equations that furnish constraints for our optimizer. And then we have this magic piece, which is the probability of collision as computed from the Poisson point process, which is given to us by the NeRF. And so this is our program, which we try and solve. There are lots of ways to potentially solve this. We tried sort of classical trajectory optimization methods where we're doing either gradient descent or Newton's method to solve these equations. We have a paper on that, and the problem is numerically it's a bit tricky, and it's quite difficult to enforce exactly this probability of collision constraint using these tools. So instead we've taken a bit of a pivot and instead looked at basically inducing an occupancy grid map from the underlying NeRF density, where the occupancy grid map is carefully constructed to embed the collision probability constraints that we're worried about. So let me tell you how that works. So essentially what we do is we take the NeRF density, which is related to the Poisson point process density, and we integrate that NeRF density over a voxel unit, and we get the probability that that voxel unit is free. There are some details in here. I see who's the mastermind behind this work going like this because I'm totally butchering the explanation. It's professor level explanation. You integrate the density over the little voxel block and you get the probability that it's free. There's a lot more in there. You can talk to him about the details. And then you do that over all the little voxel blocks in your grid, and the ones that okay, so then you get a continuous probability of occupancy, and then you threshold that probability to give a binary occupancy grid, and then you get a map that looks like this. So the block is colored in. It means that you've exceeded the probability of occupancy for that grid cell. If it's not colored in, that means you're below that constraint for probability. Great. And then you take your robot body You put a bounding sphere around it. There are a lot of ways you could potentially do this. This is the simplest and safest thing we could do. Put a bounding sphere around it, and then convolve the geometry of that bounding sphere with one of these voxel units, and you get what we're calling a kernel. And then you convolve the kernel with the intensity grid. And this is kind of the classical robotics trick of making your map fat so that you don't have to worry about the geometry of the robot. If you're not familiar with that concept, you probably will become familiar with it soon. You're given a map, and you basically buffer all of the walls of the map to make the map fatter so that you only have to worry about the center point of the robot. This is basically what we're doing here. So we're making this intensity grid fatter by the dimensions suggested by the robot, so that now we have a new grid, which we call the PER, which is the probabilistically unsafe robot region, which is robot dependent, right? It kind of convolves the geometry with the robot geometry, the scene geometry with the robot geometry. And it says, as long as the center of your robot is in free space in the PER, then the whole body of your robot is colliding with probability less than the desired probability constraint. Okay, so now we take this PER, and we've just planned trajectories through the free space of this PER. You could do this in many different ways. You could do polysplines. You could do A-star. Turns out we do A-star. And the way that we do A-star is, no, excuse me, we do both. We do A-star combined with polyspline. So we start with an A-star sort of base path, which we know to be safe. And then starting from that A-star base path, we take all the straight line segments, and we push out the sides of a rectangular prism to clear out the biggest free space that we can in this PER, right? So now we have this kind of collection of rectangular prisms that are all stuck together. And so all the space within those rectangular prisms is free space. So as long as the center of our robot stays within the union of these rectangular prisms, we're guaranteed to satisfy the collision constraint. And then we plan a polyspline optimized to be efficient for trajectory cost. So, low actuator cost and low path length and so on. And this is the planning pipeline. And so you can see now these are sort of trajectory tubes that are superimposed on that PER, and these are all guaranteed to be safe. And then then we've got our plan. Turns out this is really fast to replan on, because you're just doing A-star and this kind of geometry and then a polyspline fit. So the idea is that we'll apply this in an MPC receding horizon loop, right? So you plan your original paths, you move your robot one or two steps along there, and then your robot is moved a little bit because of model mismatch and disturbances, and so then you replan, move, and so on. So in order to do that, we need a way of localizing our robot after it takes a couple steps. So we have a guess of where it should be, which is suggested by the trajectory plan, but then it's going to stray from that plan, and we need to figure out how much it strayed from the plan and then replan, right? So now, I'm going to kind of fly through this because I think I'm probably a bit low on time. Yeah, okay. So now we have a state estimation problem. We have our robot with an onboard camera. We know where the robot should be, and we can synthesize an image that it should see because of the NeRF. This is a special property of the NeRF. You can fake images, right? So our robot should be here. We synthesize a fake image. The robot is actually here. We don't know where that is, but we take a real image here. So we have a fake image from where it should be and a real image from where it is, and we don't know where it is. And there's discrepancy, photographic discrepancy between those images. And that's what you see here in the kind of two ghosting images. One is the real image and one is the synthetic image. And then what we do is we optimize the guess of the pose based on the photographic similarity until the photographs line up as best as possible. So this is called the photometric error. We look at the pixel-wise difference between the photographs, and we basically backprop through that into the pose to align the two images. So actually what I just described is the baby version of what we do. What we do is we take that kind of mechanism, aligning the images, and we put it inside of a Kalman filter. Sort of. It's actually an optimization-based filter that's based on the Kalman filter. So we're able to estimate the full dynamical state, not just the pose. So we have 3 position variables, 3 orientation variables, 3 position velocities, and 3 orientation rates of change, right? So we have the full 12-dimensional state of the vehicle. And we assume that, so we're taking a Gaussian filter approach. So we assume that we have some prior mean and covariance over this 12-dimensional state. And then we minimize a loss function, which combines the photometric loss, that's the thing I just described, how different the images are, with the process loss or the prediction loss, which is how confident we are in our model of the robot based on its dynamics. So we have these two fighting terms, reliance on the model, reliance on the sensor. And that's inherent to Kalman filtering, right? And then we optimize this thing, which is a little tricky because it involves optimizing through the neural network weights, because you have to optimize through an image which is synthesized through the NeRF. It's okay, we can do that. We just backprop in PyTorch and so on. And then once we've optimized this thing, we obtain one 12D vector, which is the mean of the posterior distribution. And then we take the Hessian at this optimized mean value, and that becomes a covariance of the posterior distribution, actually the inverse covariance. And then we have the posterior, which becomes the prior for the next round, and we go in a loop like that. So this state estimator, there's not many state estimators that can do this, right? That can get full 12D dynamical state from images alone. But of the ones, so what we did is we took an existing method called iNeRF. I gave a little reference to iNeRF at the top of the talk. And we kind of augmented that with some Kalman filtering-like features and then compared our method to iNeRF. And so you see here our method, the mean is the solid line and the covariance is indicated by the spread. Ours is the brown and red, and the iNeRF++, if you want to say it that way, is the green. And so you see that the rotational errors are lower, translational errors are lower. They also have a tighter spread. For whatever reason, the angular rates are about the same. And the velocity errors are lower. So overall, this filter seems to be doing a lot better job. And then we stick the planner and the replanning together with the pose estimator, or the state estimator, and we do the MPC. And you see here, this is a simulation with model mismatch. So this is when you're flying with the incorrect model on the open loop plan, you hit things. When you're flying with the incorrect model on the closed loop plan, with state estimation and replanning, you can accommodate those modeling errors. Same thing with wind gusts. You can recover from wind gusts. Okay, and now we're in the process of putting all this together into a functioning autonomy stack for a drone. What I'm showing you is a piece of that. So what we've done is we've offline captured the NeRF, pre-planned the trajectory, and now we're executing the trajectory on the drone with OptiTrack feedback. So stay tuned. We're working hard right now on dropping the OptiTrack feedback and instead incorporating that online state estimator from the onboard vision. In any case, with the OptiTrack feedback, with the motion capture system feedback, it works very well, but that's not surprising. Okay, so one element of this that you might wonder about is, well, your whole planning pipeline depended on a NeRF. Where do you get the NeRF from? Why is it reasonable to expect that you have this beautiful high-fidelity 3D model before you even deploy your robot? So clearly, an important piece in this autonomy puzzle is being able to train a NeRF online as you're moving the robot around, right? So there have just in the past 6 months or so, 9 months maybe, have emerged a few online NeRF training pipelines. One of those is ours. So we basically have a set of ROS tools that implement pieces of this pipeline that then you can build on top of, right? And so we call this NeRF bridge. To be honest, there's not a whole lot of foundational research here. This is basically tool building, or the sort of merging of existing tools. So what we do for NeRF bridge is we take a SLAM pipeline to get camera poses. A little bit of a detail here. So the NeRF requires camera images and camera poses. Traditionally, those camera poses were obtained from a structure from motion preprocessing step, something called COLMAP. It's like a standard computer vision structure from motion package. And if you use any of the open source NeRF training pipelines out there, that's what they do. They take your images without poses, they put them through COLMAP to get poses, and then take the images and poses, put them in the neural network training. The problem is that the neural network training takes seconds. Like by now, not originally, but now in the state of the art, it takes within 5 or 10 seconds, you get a reasonable model, and within 30 seconds to a minute, you get a really good model. But that pre-processing, getting the poses from the images, still takes 30 to 40 minutes on modern open source packages. So we know how to solve this in robotics. This is standard. It's called SLAM, right? We can get the poses online as the robot flies around. So now what we did in NeRF Bridge is we took the SLAM package, an open source SLAM package, OrbSLAM 3, I believe, to take the camera images and obtain the poses from the sequence of images. And then we take the poses and the images and put them into a data loader for NeRF training. But we had to re-engineer the data loader because the data loader was designed to be static. It's all in the NeRF universe, it's all just batch processing, right? You take your collection of images, you put them in your neural network trainer, and boom, there's your NeRF model. So if we want to do this online, we need to have kind of a pipelined data loader where we're taking images and poses, putting them in the queue, training, popping them out of the queue, new images and poses, training, and so on. We do this in a loop. And so long story short is that now we can fly a drone with a camera on board and train NeRFs at the same time. So here is the image feed that's being used to train the NeRF. Here's the drone that you can see moving around the lab from third-person view. And here's the NeRF that's being trained in real time. So this is all, there's no pre-processing. This is really the NeRF in real time as it's being trained. You see it's very foggy at first, but as the image diversity increases, you get sharper and sharper NeRF renderings. And what's cool about this is then you can land your drone and then virtually fly around your NeRF. That's the advantage of the NeRF, right? So now suppose you're in a disaster response setting, right? And you send your drones out and they build the NeRF, and then the rescue workers can asynchronously go interrogate the model and say, what's there, is there damage here, are there survivors here? You don't need to send the drone there to get images. It's all captured in the NeRF, which then you can fly around virtually. And this all works outdoors as well. So here's an outdoor demonstration at the Elliott Center, which is a conference center on Lake Log. This is Lake Log, and here's the drone flying outside. Here's some of the SLAM pipeline that you can see the SLAM features, the orb features being visualized, and then here's the NeRF, which is the building facade of the Elliott Center that's coming into focus. Okay, so now we can plan in a NeRF, we can train NeRFs online. We're working on composing those things. Now that we can train NeRFs online as we move around and we can plan safely in a NeRF, what else might we want to do? Well, we probably want to maybe interact with the world at a higher semantic level and think about avoiding collisions with things based on semantic instructions, or think about looking for things based on semantic instructions, based on open vocabulary queries, right? So there's another tool that recently emerged, unfortunately not from my lab, although we had a lot of discussions about this kind of thing. Another lab beat us to it, Ken Goldberg and Anju Kanazawa at Berkeley. They produced this tool called LERF, which is language-embedded radiance fields. Very simple idea. You take the original NeRF idea and you supervise the training of this architecture with an extra output head, which gives you CLIP embeddings. So CLIP, I hope a lot of you already have heard about CLIP. It's an OpenAI foundation model that basically takes images and then encodes them into a latent code, which is just a vector, just a 512-dimensional vector, and it also takes natural language prompts and encodes them into the same vector space, a 512-dimensional vector, and then you can compare the two with cosine similarity with basically a dot product. And so it allows you to say, how similar is this image to this text prompt? It's a really nice fundamental tool. And so basically, in this framework, they pre-processed all the training images for the NeRF with their CLIP embeddings, with their CLIP codes, and then supervised the NeRF to embed these 2D CLIP codes into 3D, right? This is called distillation. So basically now you have a 3D field where at every 3D point you can ask, what's the semantic CLIP embedding? And then you can compare it with a query. So somebody can say, find, I don't know that CLIP knows about, but say find, And then you can computationally check all of the pixels, or you can computationally check any 3D point for its similarity to, and that collection of 3D points that are like will pop up in a heat map. And so that's the idea here, is that you have a cluttered scene, and at runtime, there was nothing that said toy elephant in the training. It was entirely at runtime, you're given a novel prompt, which is toy elephant, and you do some processing, and you can light up the 3D region in the scene, which corresponds to toy elephant. So it's a really cool, powerful tool. So we thought, well, why can't we, this is sort of research that's in action right now, why can't we, let's see, how do I explain this? Why can't we online look for something based on an open world query and train a NeRF and use the relevance between the current NeRF and the query to go collect more images to get a better idea of where that thing is that we're looking for. So the idea that would drive this is an information-seeking planner, right? We want to be able to plan a set of poses or a motion for the drone to collect images where we believe those images have high information content that's relevant to the open world query, right? So maybe the open world query is, find the dump truck. We need a way of quantifying whether this image or this image in the future is likely to have lots of information about the dump truck. We haven't taken those images yet, so we need to predict what the information content will be from those different image possibilities. So what we've come up with is the idea of quantifying the probability that any point is both occupied and relevant to the query. So the way that we get the occupancy is just by querying the density of the NeRF at that point, and the way that we get relevance is by querying the cosine similarity between the user prompt, like dump truck, and the code that's embedded in the NeRF, right? So we take that cosine similarity and you get the probability of relevance given that it's occupied. So you have probability of occupied times probability that it's relevant given that it's occupied, and you get the probability that it's occupied and relevant. And then that's a point-wise quantity, and then we consider that quantity over the whole camera frustum. We have to do it volumetrically because we don't know where the things are in that volume, right? So we integrate basically an entropy-like quantity over that camera frustum. So let me explain what I mean by an entropy-like quantity. So Shannon entropy, right, is like this way of quantifying uncertainty in a random variable. So we're basically using that concept. So here we have the density times the relevance, which is basically the probability that you're occupied and relevant, and we want to quantify the entropy in that quantity over the frustum, over this kind of pyramid that's tipped on its side. So this is just the formula for entropy. This is the probabilistic quantity and then the natural log of that probabilistic quantity integrated over the frustum. So this quantifies like how unsure are we in occupancy and relevancy over the frustum. If we're quite unsure, based on the current state of the NeRF, if we're quite unsure, well, we better go take that image so we can become more sure about it, right? Conversely, if we're very sure already based on the current state of the NeRF, then why do we need to go take that image? We don't, because it's already in the NeRF, right? So we're basically quantifying the lack of information on a camera view-by-view basis and going after the images that have low information in the current model in order to boost that information in the model. And then we wrap this around a planner, the typical sort of trajectory planning thing. So this is the entropy in the frustum. And in fact, I should have a minus sign there because I'm minimizing. So I want to maximize the entropy in the frustum. So I want to minimize the negative of the entropy in the frustum. I don't want to use too much control effort. I have some dynamics to my robots that I need to respect. And I want to stay in free space. So I have this kind of cartoony, X stay in X free, but really this could be a collision probability like I talked about at the beginning of the talk. And then you optimize this thing to find a sequence of viewpoints for your drone or for your robot. And we haven't actually implemented this yet. This is very much hot off the presses, but the idea is that we could optimize this thing in a very quick and dirty way, because it turns out these trajectory optimization problems based on information theoretic objectives are very hard to optimize. They're computationally really intensive, and the cost landscape is just really nasty. So what we would do is something quick and dirty. Just roll out a bunch of random trajectory options, score each one based on this cost function, right? And then pick the best one that's still safe. So by rolling out random control inputs, you already know that you're dynamically feasible, right? You randomly sample a whole bunch of control inputs, and then you simulate your robot's motion along those control inputs, so you get dynamic feasibility for free. And then you just have to worry about safety and then optimizing the cost that you're trying to optimize for. Okay, so that's the idea. 1 minute, okay. So then we need to be able to train the NeRF online, train the LeRF online to be able to do this in a receding horizon loop. So then this is the next piece of the puzzle, is to take what I called NeRF bridge, the ROS tool that allows us to train NeRFs online, and augment it to be LeRF bridge to train these language embedded NeRFs in real time. This is future work. There are some challenges, but we're going to try and do that. Okay, and then I'm going to talk briefly about one final idea, which is to produce kind of a reactive reasoning feedback loop by embedding a large language model within our autonomy stack. So, okay, this is a separate idea from information, so informative planning in the LeRF. That's idea one. Now, idea two, which is primarily the work of John Tucker, is you have an instruction by a human user, open world instruction. Like you're flying a drone and you say, drone, go land on that table. Now, there's a lot of ambiguity about how a drone should land on a table, and the robot has no idea how to resolve that ambiguity. So the idea is to use the common sense, to use a large language model as what we're calling a common sense core, as a way of iterating on the prompt to get more details about how it should do the thing that it's asked to do, right? And so at a high level, the idea is this: land on the table, and then we engineer a prompt for the large language model that knows that it's a quadrotor that needs to land on the table. So it says, how should a quadrotor land on a table? And the LLM comes back and says, on a clear spot, which is obvious. Any person knows you land the drone on the clear spot on the table, but the drone doesn't know that, right? You have a table that's super cluttered over here, and there's a nice clear spot here. The drone has no way of knowing that it needs to go for the clear spot. So the LLM gives us that common sense. And then we query the LeRF, not for the table, but for the clear spot on the table, which the person didn't tell us to look for the clear spot on the table. The person just said land on the table. But we do this iteration with the LLM, and we know we're looking for a clear spot on the table. We call this an affordance, right? This is how a robot should do a thing, what part of the geometry it should interact with to effectively do a thing. So we use the large language model to tell us what the right affordance is to accomplish the task. And this is real results. So we have a we have a LeRF trained of a cluttered table, which is cluttered on one side and free on the other, and we query the LeRF, clear spot on the table, and the reddest part, the most relevant part to the query is indeed the clear spot on the table. The cluttered spot is a bit orangey, so it's a bit less relevant, right? So it's kind of working. And then we, let this loose on a planner, on a robot in the lab. So here's a drone in the lab, and it will indeed go and fly and land on a clear spot on the table. So you've all seen drones flying before, so this probably isn't super illuminating, but there it is, landing on, it will land on the table. There it goes. And it lands on the clear spot on the table. So one thing that we're hoping to do with this is augment this with onboard vision on the drone, right? So yeah, from the prior LeRF model, we want to land on the clear spot on the table, but maybe we go and bring our camera to that place and we find that what was once clear now has a coffee cup there. We want to be able to be a little bit more reactive to those real world changes. Okay, so I'm gonna wrap up my talk there. I had one more segment, but clearly I completely overshot on time. And I'm just going to speed to my thank you slide. So I'm going to acknowledge all my collaborators, co-authors, and students who are the real brains behind this work. And then I'm happy to take any questions. Thanks.